All right, so we've got some people coming in here, but good morning, afternoon, evening, depending on where you're coming from. I'm Katie from Hackster, and thanks for joining us today. And welcome to the Deploying Deep Learning Inference with the OpenVINO Toolkit webinar with Intel. Stuart Christie and Shane Ya are here with us today to share a little bit about the OpenVINO Toolkit and how you can use it to build high-performance deep learning and computer vision applications. So just a little bit about our presenters today. Stuart is an IoT evangelist at Intel. He develops demos and teaches classes on computer vision, primarily for use in the retail and hospitality industries, including remote management and digital signage use cases. He is focused on the software side of the ecosystem, guiding developers building inference at the edge applications in C, C++, and Python. And he's an expert in the deployment of the Intel Distribution of OpenVINO Toolkit, media acceleration reference software, and the vPro AMT software solutions. While not working at Intel, Stuart plays with cameras and robots and builds robots with cameras. Shane Ya is a software engineer at Intel. He is responsible for creating content, conducting technical training, and supporting the developer community on Intel IoT technologies. He is skilled in developing product prototypes and demonstrations across a wide range of topics, including computer vision, cloud-based services, and broad-level communication protocols. So today's event, we're going to have 45 minutes or about 50 minutes presentation, followed by 10 to 15 minutes of Q&A, where Stuart and Shane will be answering your OpenVINO questions. So if you do have questions during the presentation, you can write them in the Q&A section. You can find that at the bottom of your screen, and we'll try to answer as many questions as possible before the end of the webinar. So thanks again for joining us, and I'm going to let Stuart get us started.
Good morning. As Katie said, I'm Stuart Christie. Currently working from home like probably everybody else, but generally I work at Intel in Chandler. So today we're going to rush through a short version of our regular training schedule. When we were doing this face-to-face, it used to take us 2 days. We go online, we shrink it to 4 hours. Today we've got 45 minutes, so we'll give you lots of material to follow up with, and hopefully we'll get some questions as we go on. So this is our attempted agenda, and we'll see if we can get how far we can get through all of this. We work for Intel. There's notes and disclaimers and legal pieces, so we shall let you see all those things. There'll be a competition or later on how those things are going. So we are enabling and changing every industry with AI, and this is some of the pieces that we work on, or that we have customers building devices. So as I say, Katie was saying, I mentioned I work a lot with the retail, digital signage. I've got a colleague that's working with fire station crews that are using OpenVINO and infrared cameras to detect what we call cold bodies, as opposed to the fires. So they're using the opposite of an infrared camera that people normally use for heat. So a large range of different pieces used for AI and deep learning. And this is probably the reason why the image recognition and speech recognition are now as good as or better than humans. And the other real factor, I think, going forward is they don't get fed up at 3 o'clock in the afternoon. These machines can work 24/7 and continue to do inspections or listen to whenever we want to some music or whatever through the Alexas or the Google Home devices. So there's a large uptake in all of these things, and OpenVINO is one of these pieces of software that allows you to build these devices at the edge. This is the usual deep learning development cycle, where you gather your data, you import it, you either build or borrow a model, you then train it for hours or days, and then you deploy it. And really that's what we're going to be talking about today, because the Intel distribution of OpenVINO allows you to run from the edge, although you can run the same models and all the pieces in a cloud system. So again, this is just the difference between deep learning training versus inference. So OpenVINO is there for inference. We use pre-trained models. And we supply a large range of pre-trained models with OpenVINO when you download it. One of the considerations for using OpenVINO is really to figure out the workload. Are you needing a system that looks at traffic going through a set of street traffic lights, or are you looking at a static car in a parking lot and trying to read a number plate on a car that's stopped in a barrier? Much different workloads, maybe the similar model, but the speed and the performance is totally different. Some of the use case requirements, OpenVINO tends to be used at the edge, and the edge could be outside. Currently in Arizona, right here, it's 103, I think. So sticking an edge device out there, you have to make sure you've got a device that can cope with the ambient temperature, or it may be in a factory in a wet area. So we have hardware available that's sealed, fanless, a range of different pieces of hardware for different use cases there. And then if you've got a system out there already, you may want to use the existing system and add AI to it. We can help with that if there's not enough performance left within the CPU device. We have got accelerators that can be plugged in either via USB or PCI slots to add more capability to an existing system without ripping the whole thing out. Hopefully there's some headroom on the device that you're working with, and you should be able to get the inference working there. But as I say, we've got capabilities of adding in multiple devices or using the GPU on your device as an accelerator if the CPU is overtaxed. I'm going to skip this slide here, although we can talk about leading. We did just bring a new processor yesterday, the 11th, or the day before, 11th gen Tiger Lake processor. At the moment, it's based really for laptops. It's a very low power, high graphics device. There will be devices in that family coming out for the embedded use case, and those ones will be available in the long lead time that the group that we work with, IoT group, will supply these devices for 10 or 15 years, as opposed to the commercial devices, commercial SKUs, which are generally 3-4 years of a lifetime. So there will be some, if you go with one of the devices from the IoT group within Intel, you can get this long life. So the OpenVINO toolkit, say, has got a large set of easy to use examples. It allows you to write once, deploy anywhere, because we can take the same model and run it on the CPU, the GPU, the FPGA accelerators, or NVIDIA's VPUs, which are video processing units. So there's a large range of processors. There's a large range of accelerators, so you can choose the best performance or the best cost device for your project. This is an overview of the whole soup to nuts piece. So you build your application using a trained model. We can take models from TensorFlow, Caffe, Kaldi, MXNet, and then ONNX. And because we're using ONNX, you can take a PyTorch model, TensorFlow 2. You can take an Apple ML model and export it to ONNX and run a model that's normally running on a phone on OpenVINO. And then we have the open model Zoo, which is over 100 open sourced and optimized pre-trained models. We call it optimized. It's actually a converter, but there's a model optimizer that will convert these models into what we call an intermediate format, IR representation. And that allows us a neutral format that we can use on all of the different pieces of hardware. We've got a set of tools. You can see them here. There's a post-training optimization tool, some deep learning streamers, OpenCV, OpenCL, code samples and demos that come with OpenVINO for doing the development. And those run on Windows, Linux, Mac OS. And then when you deploy it, the inference engine, you can do all your development on your laptop if you want. The inference engine is installed. But generally speaking, if you're talking about an edge device, you will deploy it on a separate device, or hopefully thousands of separate devices that are set up with just the inference engine and the model. And we have a tool called the deployment manager that allows you to extract these pieces from your development system and make an installation candidate for your edge device. And then you can choose at that point which plugins you need to use. If you're using just the CPU and the GPU, you don't need the rest of the plugins, so you can shrink the size of the deployment image. If you're using FPGAs but not using the GPU, you can pick and choose and vary the size of the application or the installation that goes on your edge device. Generally speaking, edge devices have got totally different processors, but different memory sizes, maybe different type of disk than say a Core i7 laptop. So the deployment manager helps you figure that out and allow you to test on the edge device and pull the answers back using our deep learning workbench to basically get yourself a test in the real world, do some benchmarking, and run all of those different batches, different sizes, change the model around if you want to at that point. And if we've even got, let's say, the post-training optimization toolkit that allows you to do 8-bit quantization if you want to shrink the model size or make the model run faster than the standard floating point 32 or floating point 16 models that generally are developed. That's the size that's used effectively for training models, is floating point 32. So I think the next stage is Shane. I'll let you introduce yourself, and we'll go on to the model optimizer and break down a bit more what this model optimizer does when it's doing the conversion. Shane, if you want to share your screen, I think that's
sure.
Yeah. Let me stop my sharing.
Okay. Share it. Okay. So we are already at the model optimizer. Okay. Cool. So everybody can see my screen now, right? We are at the model optimizer. So as Stuart just mentioned, the model optimizer is part of the OpenVINO toolkit, and that's the key components of the two, model optimizer and the inference engine. So we're showing here. So to use OpenVINO toolkit, the prerequisition is you have a pre-trained model. So which means you already have a model, you trained that, and you want to deploy the model to the Intel supported hardware, then you come to use the OpenVINO toolkit. All right, so the first thing is you want to go through the model optimizer to convert your model into the intermediate representation format, which contains two files. One is the .xml file, is the topology of their model, and the other one is the .bin file, represents the weights and the bias of your model. So basically, model optimizer is the Python-based application, so it was running through the terminal, the command line, and the model optimizer will go, when the model will read your model and will go through all the layers in the model and detect is there any unsupported layers in this model? And if all the layers are supported by model optimizer, it will do the conversion, right? If a model optimizer detected there's unsupported layer, which we named it as the custom layer, then you have to go through the custom layer process. So it's a little complex than everything was supported. So you have to register your unsupported layers to the model optimizer and write your kernel to support the operation for that custom layer. So it's advanced topic. For here, we're just assuming all the layers of your pre-trained models can be supported by model optimizer, which means everything can be converted to the IR format. Okay, and the current supported deep learning frameworks are Caffe, TensorFlow, MXNet, and ONNX and KLD. For those not supported directly by Model Optimizer, you can always convert it to the ONNX and then convert the ONNX model to the Model Optimizer to the IR format. And the reason you need to convert it is the IR format is the only accepted format that inference engine can recognize. So after you convert your model, you need to, in your application, you need to call the inference engine API to run this model. So you have to have a IR format. Okay. And other than only converting your model to this IR format, Model Optimizer also having some optimization to this model, and it also can quantize the model's weights file. So let's look at the optimization techniques. So we know
I'm not seeing, Shane, I'm not seeing your slides change.
So how about now?
It's still stuck on just the main Model Optimizer one.
How about now?
There we go.
That's it. Yep. Now we're in play
And
mode.
it's moving, right?
Yeah.
Okay, cool. Awesome. Thank you. All right. So where are we? Okay. So we see Model Optimizer can do the optimization to your pre-trained models. So basically, we know inference is only the forward propagation of your data, right, through this model, right? And for training, it also has the backward propagation, and it will adjust the weights and bias. For a pre-trained model, those weights and bias are already fixed, so there's no backward propagation. So that's only the forward propagation for your data inputted to this model. And there's several layers are unused during inference. So Model Optimizer will detecting those layers and automatically drop them out. So which in the runtime, you will have less layers to run through your hardware, right? And the other type of optimization is Model Optimizer will detect if there are like similar operations or the several layers are doing the similar operations, and they will find detecting those operations and combine them into one. So that's also automatically done to your pre-trained model. To run the Model Optimizer, the simplest way is to run this Python application, and then at least you need to put one argument is this input model, and putting the directory, the path of your pre-trained models, and give it to the Model Optimizer, and then it will automatically convert that. But there's more arguments you can use for the Model Optimizer. So we'll show that in the next few slides. All right. So this is the most used optimization techniques, which is named linear operation fusing. So basically 3 stages in this technique. So step 1 is Model Optimizer will detecting if there's batch normalization or scale shift layers in your pre-trained model. And if there's this 2 type of layers, and it will doing the decomposition. So making this 2 layers into the multiply to add sequence. And the second stage is linear operation merge. So it will merge all the multiply to add into one instance, into a single instance, right? And then the third step is linear operation fusion. So it will fuse the multiply and add operations to the convolution of fully connected layers prior to the batch normalization layer. So on the right side, you can see this is the Caffe ResNet 269 network, part of the network, right? And this portion you see after the convolution layer, there's a batch normalization and the scale shift. So after applying Model Optimizer, those 2 layers was fused into the convolution layer. So the IR format will has a 2 layer less than the original model, right? And so Model Optimizer optimization is the hardware agnostic. So at this point, you have not decided which hardware you're going to run the model, right? It will run the inference. So it's already helped you to reduce the several layers. It can be fused into one. And then when you decided which hardware you're going to run the inference, you're loading the converted model to that hardware, to that plugin. And then the runtime, the hardware library is actually the full implementation of that inference. We're detecting there's other few layers can be run fused into one. So they will do that during the runtime. So that's another level of optimization. which was run by the inference engine, not by the model optimizer. So after these two steps of optimization, in the example, so originally you have 4 layers. After model optimizer, you have 3, right? This batch normalization was fused into convolution, and then you load this IR file to the, for example, CPU plugin, and then CPU plugin detected this ReLU also can be fused into convolution. So eventually, during the runtime, you have only 2 layers running on CPU, so which will reduce the computation time. Okay. So the second part is the hardware related, because you already decided which hardware you're going to run the inference, right? You load that. The other type of optimization is framework or topology specific optimization. So like the group convolution fusing, it's only applied to the TensorFlow topology. And this ResNet optimization is only applied to the ResNet. Well, I'm sorry. So group convolution fusing only applied to TensorFlow framework. And this ResNet optimization only applied to a ResNet topology. And if you don't want to run those kind of optimization automatically, you always can disable that. So you can put the disable argument to the model optimizer. All right, and another thing a model optimizer can do to your pre-trained model is quantize. So if you put the data type argument and put the FP16 or FP32 after this argument, model optimizer will help to quantize your pre-trained models into this 2 type of data type, and the half is equals to FP16, float equals to FP32, right? And then so the reason we want to quantize our pre-trained model is, one, it can reduce the footprint of your model. So if you convert a model to the FP16, it will have a half size of the weight file than the FP32, right? And the other reason is some of the hardware only can use one type of the data type, like the VPU, the neural computer stick, right? For example, they only recognize the FP16 data type. So you have to, if you want to use the model inferencing on the VPUs, you have to convert or quantize the model to the FP16 first. Otherwise, it won't run. And there's also even lower data type, like the int8 or this BF16 only works for some certain type of the Xeon CPU. So this int8 you cannot convert it through a model optimizer, because if you convert all the layers to the int8, the accuracy of your model might be dropped. So you need to provide a data set and convert this model to int8 through a tool called post-training optimization tool, and with your data set provided, and then it will help to decide either which layers need to be converted to the int8 and which layers maintain the full precision to make sure the accuracy of your model did not drop dramatically. All right. And that's the post-training optimization tool. So to use this tool, you still need to use the model optimizer to convert the model to the full precision IR, which is the FP32, right? And then you put this FP32 IR format model and with your data set into this post-training optimization. And then it will help to do the accuracy and performance check and generating the int8. Also, you can set the percentage of the accuracy drop you can accept it through after converting it to int8. Okay. If you're a developer and you don't have your own model yet, and so this is a place you can try to use those pre-trained models, either trained by Intel or by the public. So this is called Open Model Zoo. So you can go to this Open Model Zoo on the GitHub and downloading those pre-trained models. So there's a tool called Model Downloader, pre-installed by the OpenVINO toolkit, and you can use that Python application to download the available pre-trained models from the Open Model Zoo, and also that tool providing the accuracy checker. So if you have the random data set or you have a real data set, you can use that with the accuracy checker to check how accuracy of this pre-trained model. So the pre-trained models are 2 places you can find that. One is if you install OpenVINO toolkit, it's already there, so it's within the installation package, or you can obviously check the latest version on the GitHub repo. Okay, so I think that's a quick overview of the model optimizer. Stuart, I give it to you.
So we've had a couple of questions come in, and there's a few there that are applying to this. One of them was, can he just download a model from the Model Zoo, or does he need to get like the Cafe framework to get it going? So say, we'll just answer that and say that, yeah, all the Model Zoo models are standalone. If you've got the framework and you want to, change the model around, or if you want to do stuff, then you can use the framework. You can run certain layers, inside TensorFlow, for example, and then have the rest accelerated by OpenVINO. If you want to do that hybrid sort of piece, but yeah, if you're just starting with a pre-trained model, there's no need for the original framework to be downloaded. So let me see how I get to my slides. So we're going to do the inference engine. So I'm going to skip through. Sorry, I should have done this while I was offline. There we go, inference engine. So this slide here shows the.
You want to share your screen, Stuart?
That would help, wouldn't it? Yeah. Now we've got to find Zoom again. Should you seeing it now? Should be.
Yep, looks great.
Most of the slides are blue, so I can't really describe it. It says Intel Deep Learning Deployment Toolkit.
Yes.
So on the left-hand side, you can see the trained models that we support: Cafe, TensorFlow, MXNet, ONNX, and then called the model optimizer that Shane just talked about, and then the IR data, the intermediate representation. So on the right is the inference engine, and that's what I'm going to be talking about now. So it's got several different pieces to it. There's one API, actually two APIs. There's a C++, or C++, and a Python. So 3 APIs, and we've got models that can be used with Go as well, using the same API. It's a dynamically loaded plugins for each piece of hardware. So we've got, let's see, we've got 6 there. So the CPU plugin, the integrated GPU plugin, an FPGA plugin for Altera Intel FPGAs, and then the Myriad plugin is used for the Intel NCS, so the NCS2 USB devices, or sort of devices in that single form factor. And then we've got one we call HDDL, and that's for boards that are built with multiple multiple Myriad devices. 4 or 8 of these devices that are used in the NCS on the HDDL board, and that plugin is used for those. And then the GNA plugin is the Gaussian network one for the Caldi pieces for the audio. So it really depends on what device you want to run your model on, but you can run it on multiple. You can do various different things to get them to run in parallel or sequential. So we'll cover that a bit later. Let's go to the next slide. There we go. So this is a sort of slightly different view. You can see here, you've got one application with a common API to choose all of the different pieces. And the plugins, you can see there, there's a bit more detail on them. So the processor or the CPU plugin is using the math kernel libraries. They're software intrinsic, so in fact, little pieces of assembly language that run on all of the different CPUs. It's either a DLL or a shared library, depending on the operating system. For the graphics for the GPUs that run on the Intel Iris pieces, and also on the new XE pieces there's a CLDNN plugin. So that's OpenCL with the deep learning neural network plugin. As I say, it's developed in OpenCL. The GNA plugin's got a separate GNA API. And then the Myriad and HDDL plugins use the Movidius API underneath. And then for the FPGA plugins, we've got what we call a deep learning accelerator plugin. So all of these plugins sort of convert the model into specific pieces that run on each of these devices. So it's done automatically. You don't need to do any of the the work. It's mostly open source. There is an open source version of OpenVINO. So if you look at it, that's why it's called the Intel Distribution of OpenVINO toolkit. So there is an open source distribution, and it's available at the OpenCV repo, which is also where the model zoo is stored. So the way the libraries work, we create an inference engine core object to work with devices. We read the network in, manipulate the network information, so scale the image or move the colors around to suit the model that you've chosen. They may need height by width instead of width by height, for example. And then we execute, we create some buffers and execute the inference from the input image and then the answer coming back through the output buffers. And if you see in the next slide, this is a bit more detail on how that's done. So the little bits of code there are actual the code that we use. So we create the inference engine core object with, we call it, in this instance, it's called an IE object. We read the XML and bin file using that IE read network call. We prepare the input and output buffers, these input blobs and output blobs, and it reads it from the network. So the net.inputs and the net.outputs are set up to contain those different requirements that each model has. Then we load the network to the particular device, and the CPU, the GPU, or one of these PCI devices, using that load network call. We prepare the input frame. So we talked about resizing it. We may have to transpose some of the colors. Some of the models require different, well, all of the models require different sizes of images. There are some semi-standard numbers. You'll see a lot of 224s in the names of these models, and that's generally speaking the size of the image. So take your nice big HD 1080p image and shrink it down to 224 by 224, and then, as I say, maybe change some of the colors around, or the height and the width. We're using OpenCV here in that CV2 resize, the transpose and reshape calls to do that. So OpenCV is installed with OpenVINO. And then when we actually run the inference, we give it the input blob with the frame in it, and run the inference and then process the results. Generally speaking, the results come out are very model dependent. And then if it's a video application, we run through every image until we're completed. So we run through that loop. Let's say there's a link there at the bottom and it's got all the APIs. With OpenVINO, there are a set of demos and samples that show how to call the APIs in both C, C++, actually, not just both, in all, C++, C, and Python. So there's a set of examples there installed with OpenVINO that allow you to see how to use it, ranging from simple hello world ones through some slightly more complicated things like eye tracking and pieces like that, chained models effectively. So this shows the different types of models generally that we're shipping with OpenVINO. There are three particular pieces: classification, detection, and segmentation. And it starts from left to right. It's the quicker, faster, easier ones. The segmentation one on the right takes more time, tends to be a bigger model, more processing power. So classification on the left, the answer coming back from the model is generally a set of labels or numbers with a confidence level. So in this instance, it's detected person, sheep, and dog, but doesn't say 5 sheep. It just says, okay, there's a sheep here, there's a person, and there's a dog. And if the threshold level is set at 50% or whatever, then we'll display that on the screen. The detection model in the center, it's found 5 separate sheep, yeah, 5, 1 person and the dog, and you can see there they're different colors, so they've got different labels that have come back, and the boxes that have been drawn by OpenCV are because the model will send back an X and Y location for each object that it detects in the image. So there'll be a X and Y bottom corner, X, Y top corner, and then we use that to draw a box. So it's, say, a bit more time to do that, slightly more data. There could be more than 7 objects coming back because the system may be detecting several other things at maybe, say, a 10% confidence level. But generally speaking, again, you set the confidence level and you go with it. Most of our examples and everything are set to either 50 or 70% confidence level. And then the segmentation model, there's a lot more data coming back from that. If you see there, each sheep is effectively isolated different colors. So there's 7 bitmaps that are sent back from that model that allow us to draw the bit, scale it back up and draw on the original photograph and give you pixel by pixel accuracy. So a lot more accuracy than the bounding box from the detection model. So segmentation models tend to run slower, obviously, because they're doing that, but there's a lot more data that comes back. I mean, it's a 224 by 224 matrix that's sent back, and then we can encode it because it's really just binary. But it still takes a fair bit more information to send back a segmentation model than the others. So when we get these answers back, this is how we process the results. So this one shows a detection one with the bounding boxes. So if you see on the left there, the format that's coming back is, we've detected 7 objects. So was it 5 sheep, a dog, and a guy? And the image ID is the actual image itself, because the system can be processing multiple images at the same time. So this is an ID for that particular image or that frame. A label, which is the class ID. There's a label file that's supplied with the model that has the index 1 is a man, index 2 is a sheep, and index 3 is a dog. So that's something that you check. Basically, go back and say, okay, that's good. There's a confidence level, 50, 70% or so, and then the X and Y locations of the top left and the bottom right bounding corner. And we use OpenCV in all of our examples to draw these boxes, and you see the code on the right. So you can call these routines from the existing samples that are shipped with OpenVINO to, if you just want to change the colors or you want to do something different, or if you want to, in this instance, we're writing out the image with the boxes to a file. So that can be done as well. Generally speaking, we're using these sort of samples so that you can see that it's working. If you think about it, really, this is supposed to be computer vision. We're not supposed to be looking at the answers. The computer is supposed to be looking at the answers and sending back just the data, and we process the data and not the actual image. But obviously, to see that your model's working, you need to look at it yourself. But if it's you're counting cars going through a set of traffic lights to look at congestion, you just need a congestion number and not an actual count of the cars. You don't need to look at the cars going through unless you're wanting to read number plates and things like that. So there's different variations on what you're wanting to do with the data. But generally speaking, I think the only one where we actually think you would use the vision itself is things like a security system, where the model itself would detect, a person or something that needs to be detected, and then would highlight it on the screen and alert the user so that they can make a decision. It may automatically raise an alarm, but generally speaking, that's about the only ones that we see that have no people looking at the screens at the same time as the computer. So the inference engine can be run in several different ways. Generally, when we start off, if we're looking at a simple sample for learning, we use what we call the synchronous API, and you see that there. It does a transfer of an image. It does an inference of number one, and then the next thing is it transfers image number two into the inference engine and runs inference number two. And the time is the time, or the frames per second is the total time of the transfer and the inference. We can speed this up with the async API, where we read in a transfer, and while we're running the inference, we pull in the data for the next frame. We can also, when we run inference number two, we can pull in the data for inference number three, the transfer number three, and post-process the answer for the transfer number two. So there's now some time basically available to run on the multi-core processor, the scaling, the drawing of the bounding boxes, while the inference is running on the next frame TBD. Let's see. There's another mode available, basically because we've got multi-core processors these days. You can run multiple streams, which runs effectively inference requests in parallel. And we set that with a parameter called throughput streams, and that allows you to run multiple inference requests simultaneously. We have an API that you can call that will give you back the answers. How many inference streams can this particular device run? So you can, programmatically choose the best version for your model. One other sort of wrinkle within the inference engine is the capability we're calling here heterogeneous support. So the FPGA devices do not support all of the layers that the CPU or even the GPU support. They're programmable, they're field programmable obviously, but they just don't support all of those. So if there's a layer that needs to be run that's not supported by the FPGA, using this hetero plugin, we can fall back to one of the devices that can support that particular layer. So we can fall back from the FPGA to the GPU, the Myriad, or the HDDL card, and run it on there. So it's used for to get the system to work, but it also can be used with there's an affinity piece that can lock down a particular layer to a particular device. So if you're developing a custom layer, we've got tools to help you develop custom layers. You can tell it to run the custom layer on just the CPU, and then use the debugger and everything there before you implement it on the FPGA. So there's different tools available to allow those ones. And then there's another one that we call the multi-device. So if you've got, generally speaking, you've got a CPU, a GPU, and you may even have plugged in a Myriad device, you can use the multi option on the command line, and that will do a sort of round-robin test to see which device is available and run the next inference on that device. So it's a sort of poor man load balancing piece. It just uses the next device that's available in the priority list that you give it. So it allows you to use all of the devices up to obviously the thermal limit of your system to keep them fully running all of these inference requests. These are some of the demo applications that we ship with OpenVINO. So a smart classroom one for that recognizes actions. So now somebody stands up, it will recognize them standing up or raising their hand. There's a multi-camera, multi-person example that tracks multiple people on multiple cameras. So you can use it for public safety, but it's also quite useful for like a store that's got multiple cameras and doing person counting. They don't want to count this person every time he enters a different camera, so they can track people from camera to camera. Set up the threshold and say, okay, if they've been gone for 5 minutes, it's a new person, or they've come back, it's a 7. He's actually left the store and come back again. Gaze estimation. So that is used by digital signage people to figure out if you're actually looking at an advert. So we would detect the face, and then the gaze estimation, the head pose, can be used to determine if somebody's how long people are looking at a particular sign or piece there. And then the weld porosity detection is one for finding welds in defects in welding. And then the person in painting removes unwanted people in images or videos. So that's a fun one to use for your friends. And say that there's a set of demo applications as part of the Model Zoo. So if you do a Git clone on the Model Zoo, you get all the demo applications as well. So what are we doing on time? 9:48.
Yeah, we have about 7 questions currently that are open. Shane's been doing a great job of answering a lot of those questions while you've been chatting, Stuart. So is there any, did you have an opportunity to have like a model, or is there somewhere with that Model Zoo, can people go there and see it in action? Is that?
No, I mean, the Model Zoo really isn't a zoo full of working models. It's just the name that these deep learning people use for, there are TensorFlow model zoos, there's OpenVINO model zoos. You go there and you can have a look at the actual, the website. We can actually see if I can flip over to that and get the,
no
the website. Let's see, what Model Zoo? Can you see my screen now with the Open Model Zoo?
Yeah, great.
Yeah. So there it is, right? And there's a list of all the models. And if you go and click on, say, MobileNet, there's one here. You get a description of it. You get specifications, the input and output requirements, main values and scale factors that you need to put into it to get it working, and then what comes back, the batch size and the vector of probabilities. So this is this one would be, say it's finding, it's looking for 20 different things. It will send back 20 different numbers and a confidence level that there are these things within that image.
Great.
And say each different model's got different pieces.
Thanks for the explanation. Did you have a couple more things you wanted to go over? We have, I think, a few questions that we could.
I think we just do the questions. Unless, Shane, what do you think? We've got like 10 minutes.
10 minutes,
10 minutes
so we have
left.
some time.
Yeah. Let's just do the Q&A. Yeah.
Yeah, let's do the Q&A live then. Let's see, will there be a demonstration? We'll have a showcase. I don't think we've got time for a demonstration, unless Shane, you could maybe run up the
DevCloud?
DevCloud? Yeah.
Yeah.
Yeah, we have a piece of hardware, well, not a piece of hardware, a warehouse full of hardware, over 200 devices, 214 Intel devices that are available for remote access. Do I have to stop sharing?
I think so.
Yeah.
Okay.
So 214 devices that can be used remotely. You can log on, you get a Python notebook, you can run a lot of these examples we were talking about before. So now you're seeing Shane's screen,
so
and this is the dev cloud.
Yeah.
So we could run a quick sample on there.
I'm going to run the tutorial, objective of tutorial. So that one should, this one is showing the Inference Engine API. So you need to import a few libraries and read the model. So in this example, the model already downloaded there. So just need to use the Inference Engine API to read this model, and you decide which device you want to run this model, run the inference, right? And then you load this model, you create the Inference Engine core object, and then using the function of this object to load the model, read the model, and to make it running on the device you selected. So I already did that. And for this example, we're going to inference this image, right? And let's do that. So the inference time is only 14 milliseconds, and then we want to process the result. So that's the customer or user-defined function. So the model only gives you this type of output, but how to use that output, it's all up to the user. So either you can draw a bounding box on the detected objects, or you can do something creative on the output. So for example, this one only drawing the bounding box on the detected vehicles here. And you can also run a different image with the same model, if the model also detecting the object. So for example, this one is using MobileNet SSD. It can detect the human and detect the vehicle. So you change it to the image to a human image, and they will detect that there's a human there. And we can skip the running image, and we can run also run the video. For the video, because OpenCV is also pre-installed within the OpenVINO toolkit. So you can, using the OpenCV APIs, to read the video file or read the camera directly. So this is the video, the car running on the road video, and we're just using the same model to detecting this moving part. So this is like a really quick walkthrough of the
quick demo. Yeah, exactly.
Yeah. So this is give you just like a demonstration of how to use the model. So with the Inference Engine API. Yeah.
Yeah. So let's see. Somebody was asking, is the Inference Engine supported for x86 based mobile chipsets? Yes, it is. It's running on my laptop. So yeah, mobile chipsets. The nice thing about the mobile devices is, generally speaking, they have an integrated GPU, and you can use the CPU and the GPU, either one or the other or both at the same time, using these multi plugins that we've got. We've got, how can the POT help in improving inferencing?
Right.
You want to answer that one, Shane?
Yeah, I'm trying to type in that, because if you convert a model to int8, it will not only improving the latency and also improving the inference time. It gets a better FPS. So yes, the answer is yes.
Yeah, you will lose some accuracy because you're going from, say, a floating point 32 to an 8-bit integer, and the tool within the POT tool allows you to specify two different modes of operation. One is convert everything to int8, just see what happens, and that's as fast as it will ever get. The other one is like, I only want to lose 0.5% accuracy. So you need a set of data to measure the original accuracy, and then the tool goes through and keeps converting bits to the int8 until it either it's finished or the accuracy drops below that, just above that 0.5, and so you can get a speed up, but not the complete speed up, because you're more interested in the accuracy. So it can be used in the two different modes. It's a nice, easy GUI using the deep learning workbench that allows you to load the models from the model zoo. You need to supply it with a data set, but it could be a data set from, we're using Cocoa. In fact, there's it coming up now.
Yep. So this is what Stuart just mentioned. So if you want to, this is using deep learning workbench, but that's using the POT at the underlying, right, at the backend. So when you're converting a model to int8, there's two options. You can convert as many of layers you want to int8, then that will have no control for the accuracy drop. Other method is you can control the accuracy drop to which percentage you can accept, and also you can select how much of the percentage of your data set you want to use to convert this model to int8. So after you did that, and this is the MobileNet and that SSD converted to int8. So it was the mixed precision of the data, right? You can int8 and FP32, FP16, and that one will give you the better total throughput, right? A better FPS, and also have a better latency. And you can also use this tool to check the accuracy. And for the original model, before we convert to the Int 8, it's like 67% of accuracy. After that, it is 60.57. So it's within 1% of the accuracy drop, matches what we said. So yeah, that's just a quick demo of that.
Yeah. There was a question there from Alex saying he's using multiple models loaded onto the HDDL plugin, which is the one with the multiple myriad devices. And he finds that the HDL seems to unload and load models during runtime. Is there a maximum model usage that can be loaded onto myriad? Yeah, there is, because there's a 4 gig, I think it's 4 gigabytes of RAM on a myriad, and it's all contained within the myriad. So if the model itself is no, too big, then it won't be going there. You can, he says that the loading and unloading slows down his application, which is true. You can speed it up. There's when the models start, they are in the inference engine for the GPU and the myriad devices use OpenCL as the generate the plugin or the model, the inference engine. Sorry, these can be they do a just-in-time build. So every time you start it, it builds it. Now it will cache it if you're using multiple models going back. So you don't really have to do it every time. But what you can also do is load it once and then unload the pre-compiled version and use the pre-compiled version with your as the inference piece. So rather than give it the whole thing in OpenCL and then have it converted into an OpenCL kernel, you can just load and unload the kernels. So if you look at the API for, I can't remember what it's called, I'll maybe track it down, but that would speed up that loading and unloading. Trying to make it smaller is kind of difficult because we can only do FP16. We can't run Int 8 on the
NCS2.
NCS2, yeah. So
yeah, currently only support on CPU and GPU.
Yeah. So you need to find smaller models, Alex. Sorry. Let's see what other questions.
I think we maybe have time for like one more quick question because we're at the
minute there.
Yeah, we got about a minute left, but yeah, just go ahead and do one more quick question, and then I'll finish up with a little bit of information about the contest that we're running as well.
Yeah, sure. Let's see what else we got.
Stuart, you have the experience on Raspberry Pi, right? Can you use the multiple plugin along Raspberry Pi?
I've used multiple sticks.
Yeah, that's the question. Yeah, because I answered that, but I just want to make sure with you.
Yes, I don't know. It was an older version. I think it was before the multi plugin came in. I will find the GitHub link and we'll post it on the answers, because we're going to post out this recording and the Q&A after this event, which I think just went bing, 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 and I think our time is up. Yeah.
So no problem. We'll just, like Stuart said, we will be sending out a recording and everything after in an email once that's up on our YouTube channel. I also wanted to point out that we are doing an OpenVINO contest right now on Hackster.io, and so I put that link in the chat. It's Hackster.io/contest/DL Superheroes. So you can go and check that out and see what you can do with OpenVINO for a lot of different applications. I think there's 5 different categories that we have going on there. So if you have any questions regarding the contest or anything, you can send Hackster a message at contests@hackster.io. So I will also put that in the chat right now as well. So if you do have any questions, just email us there and we'll have all of these resources for you after the event. So thank you so much, Stuart and Shane, for joining today, and we just appreciate your time.
Well, you're welcome.
Yeah.
One of the things, if you submit an attempt or a competition submission. There we go. Project. Yes, that's the right word. I think there's an early submission date, and the first, I think it's 100 or so, will get an NCS2 stick.
Yeah.
And I think if you do it this week,
September 21st, I think is the deadline.
The actual close date is in October for the competition, but if you submit and start now, you'll get you put in for one of those. And I think you also get some Hackster swag this week.
Maybe.
Yep. I think you did. Yeah, if you sign up this week.
100% sure on that, but it's on the contest page if so you can go check out that contest page and we will have all the details there for you. And there's also a discussion forum that you can ask questions on there as well. So
yeah, that's true. So Shane and I are often on there answering questions as well. So if you didn't get your question answered here and we don't answer it later, please post it on the competition.
There we go. Jessica just answered swag bags. So yes.
Oh, yeah.
All right.
Cool.
Excellent. Thank you, everyone. We really appreciate you joining us today, and we hope you have a great rest of your day or evening wherever you are.
Yeah, have a nice holiday
weekend.
Yeah, it's a nice weekend for us. I think I'll start now. Yeah.
Great. Thank you all.
All right.
Bye.
Bye then.
Bye.